So this is the content of my talk. So first a couple of general words about my research and what is my background, why I'm talking like I'm talking. So then about naturalistic approach in human neuroscience, how we use films, music and narratives to study the brain. And then so one of my favorite studies, what we have done is the brain-to-brain coupling of emotional speech. So how my brain influences your brains now. Brain activity during listening and seeing, lip reading, speech, the same narrative. So this is a kind of back to the basics because so I used to study audiovisual speech for many years at least, so before moving to some other topics. And so the next topic is from shared to individual interpretation of narrative. And so a little bit about the conversation analysis and psychophysiology, once again combining two very different fields. And so now we have had some relatively interesting results. Take home message and then future directions. So let's see where we are approximately after 1 hour. So general context. So this is how I think. So I think that reality is socially constructed, right? And how we perceive and understand the world is an agreement with our conspecifics. So this is actually something which is very much related to what we heard already today. So how we perceive the reality depends on our perspective, the context and the situation, and this is a very big challenge to experimental cognitive neuroscience in my opinion. And so I also want to mention my Russian connection because now when I'm here, so one of the basic ways of my thinking is that I think that behavior it should be regarded always as goal-directed. It's not actually so directed by the stimuli, but it's directed by where it goes. So, and there are, of course, so many in the audience know very well the theory of functional systems and Piotr Anochin, who is one of my heroes. I have many other heroes also. And so very important part, so in my thinking, so very important for my thinking has been the collaboration with Professor Yuri Alexander from the Russian Academy of Sciences, and so the previous boss of this laboratory, Slava Svirko. So both of these gentlemen have visited actually many times Finland. And then I'm really pleased to also have the chance to collaborate with Yevgeny Nikolaevich Sokolov because he was one of the most brilliant persons I've ever met. So sometimes, this group of people and then Yevgeny Nikolaevich were not in total agreement, but that's another story. Some of you might know something about it. But eventually they actually they appreciate very much each other. So this is how I started my brain research. Mismatch responses to peeps. How the brain reacts to peeps. It was a long time ago. At that time, actually, so we didn't have the fascinating, the modern brain, the brain imaging methods, so what we have now. So it was very simple, 2 or 3 EEG electrodes, and then so trying to figure out what is happening in the brain when we detect changes in our surroundings. So eventually we moved from tone peeps, of course, to speech stimuli. So back, ga, and things like that, and so still continued. So this kind of mismatch responses. Then at some point, so we moved to kind of more.
Yippee.
This is pretty loud.
Yippee.
So more naturalistic stimuli here we studied actually using the McGurk effect, so the audio-visual integration. And then, so nowadays we have used quite a bit movies, and this is actually self-production, so originally meant to study actually the brain activity in psychopathic people. And so this is from our perhaps most recent line of research where they're studying body responses and conversation between two people, a dyadic interaction. And so we have, in this case, here we see actually GSR signal, from this whole subject, and then how they co-vary, so these two people are telling stories to each other. I will tell you about this just shortly. So what is naturalistic neuroscience? So the stimuli are something like this. Music, tango. So, wonderful piazzolla. Very good, very good. Correct answer.
Uit tänään pitkää matkaa ja olet jo hyvässä vauhdissa.
normal speed.
Allas- ja kuntouimareille varattu rata on melkein tyhjä.
And sometimes we actually also see the persons.
Havahduin herätyskellon sinnikkääseen pirinään. Herääminen tuntui raskaalta, mutta pakotin itseni ylös sängystä.
And then we measure the brain activity, and nowadays we basically use functional magnetic resonance imaging. We also use MEG. I used to actually use EEG and MEG for decades, but so the recent research has been done using fMRI. So I don't tell about these imaging modalities too much. So we just measure the brain activity in a certain way. So if you want to ask about the details, so please ask this. So then we record brain activity from many brains. So in the scanner, not simultaneously, of course, use complicated stimuli, music or whatever, and then we use the method what is called intersubject correlation, and I will shortly describe that after a while. So actually, I described it here. So what we are studying is the similarity of the brain activity in the various subjects. Not the strength of the brain activity, but similarity of the brain activity, and in this case, it's the both signal, similarity in the both signal. And so here, this is how it goes. So we have three subjects here, A, B, and C. Then we focus in this case what is happening in the auditory cortex. The subject, for example, are viewing a film, record signals from the auditory cortices, and then we overlay them here. So it's a little bit like EEG signal or MEG signal, it's much lower. And as you can readily see, when they are listening to the same soundtrack of the film, so the signals are pretty similar. So then what we do is very simply we calculate the correlation between the signals. Actually, originally this wasn't our idea. It comes from Uri Hassin's laboratory from Princeton University. So first we calculate pairwise correlations between these two, and these two subjects, and from that, on the basis of that, we calculate mean intersubject correlation between the subject, and then we construct maps, brain maps. And now it is important that so when we construct these maps, it's the similarity of the brain activity. It's not the strength of the brain activity. So, for example, even so the synchronous very small signals, if the signal-to-noise ratio is good enough, creates a very strong similarity in the brain activity. And this is a very important feature of this method. So now I show you something which I think is an ideal way to study the human brain under naturalistic conditions. No, it's supernaturalistic conditions. So it's not naturalistic, but so this is how I would like to do that in the fMRI scanner. It's possible, but this requires a little bit more work to be done. So this is what we have already done. So we have used group ICA to calculate brain structures on the basis of connectivity pattern in the brain. And so if you do that, so this is what you get. So without using the anatomy atlas, you can find, for example, auditory cortices, motor cortices of the right and left hemisphere, lateral occipital cortex right, occipital cortex left, and so on and so on. The point being, actually, so this comes from our subject's brains. So what I would like to actually have, and many, of course, so doing this kind of research would have the same from individual brains, so that actually, so we have a very good quality map. So about the functional anatomy of the brains of the individual subject, but this requires some more research to be done. So in our research, then we have actually, so when finding the areas in the brain, we have started to study the connectivity between the brain areas. And as you know, so one of the basic principles how the brain works is that how different parts of the brain are connected to each other. This is also valid, for example, the auditory cortex. Auditory cortex is doing many things because it's connected to so many different parts of the brain. So let's move on. And then so if everything goes well, so then we have a very detailed understanding of the single human brain. So this is actually the average brain. So now I'm talking about what will be in the future. And then when we have actually good understanding of the different parts of the brain, using whatever methods, so then we start playing with the stimulation, and this is how the different parts of the brain are connected You should see some lines there, for example here, where the subject are listening to this kind of rock and roll music. This music is much nicer. It's piazzolla, but the same thing is there. And of course now so the point is that we are comparing the connectivity patterns depending on the different types of the music and trying to find some differences and commonalities. And then we have rite of spring, so different types of music. So finding the anatomical locations and studying the connectivity between different parts of the brain. So here you see a little bit better. So let's go here. What happens in the brain with the subject? Now you, because you hear this music. So how their brains are, and your brains are activated just now when you listen to this music. For example, now, for some reason, the visual cortex of the left and right hemisphere are connected with each other, but also some other parts of the brain. It's a very dynamic pattern what we see when we have this kind of naturalistic stimulation. And now the point, of course, is that so what I show here is all the connections are highly statistically significant, whatever it means. So in this specific experiment, then we actually are comparing the brains of the musicians and normals, so to say, to see whether there are expertise-related differences in the brain activity. And so they are. I don't so want to tease you with these movies anymore. I just show the results. And for example, so this shows the increased connectivity of brain networks, especially in the musicians. Here the subject are listening to Stravinsky, beautiful Stravinsky music. And here we see so brain from the bottom, and so what we see here is that so in the musicians, a stronger connectivity pattern between the left and right auditory cortices. So then we jump over so this modern rock and roll to Piazzolla, the same thing, or the same thing being that also when the subject are listening to Piazzolla, the left and right auditory cortices of the musicians are connected more strongly than those of non-musicians. But in addition, we start to see some interesting things. So now actually, so there are also a stronger connection between the auditory cortex and premotor cortical areas here and here. So these are perhaps closer to the primary motor areas, and this is closer to the speech-related motor cortical areas, but also to cerebellum. So there are differences depending on the music, and so activity pattern depends on the music we are listening to, and also we see differences related to the expertise of the subject, which we are very carefully characterized in this experiment. Now we move to happy emotions. I like to use this slide because it shows the very important principle of emotions being contagious. You see smiling, beautiful young people, and you feel a little bit better. So this is the experiment. So we had film clips depicting different emotions, altogether 13, which varied in valence and arousal level. So this is an example. One clip, which might already now be familiar to many of you. So the subject you are now viewing this film. And this is the intercept correlation across your brains. When the film starts, so basically the activity is here in the occipital cortical areas, of course, because you see something. But the intensity is increasing in the film, right? Activity is spreading to more frontal areas, now in parietal areas, in the premotor cortex. Music, of course, is very efficient here. Something terrible is happening, so the similarity of the brain activity now related to this negative emotions is increasing. I'm sure that you can take it, okay? And now, so this is the climax of the film. Very strong correlation with the visual cortical areas, but also in many other parts of the brain. So basically, this was the experiment using different types of emotional clips. And so in these experiments, it's of course always important actually to try to have actually the measure the experiences of the subject. And in this case, so then after showing the film, we asked the subject to rate the valence of these film clips and rate the arousal level of these film clips, and then use this information to see how the similarity in the brain co-varies with the experienced valence and arousal. This is the way to go there. So in these experiments, it is crucial also to study the experience of the subject, and of course this is the difficult part, because so there are trillions of ways of doing that. But you have to choose what you want to understand and then measure that. So once again, so intersubject correlation across so let's say 30 subjects. So with the red color you see always when you see the red color, there's a significant intersubject correlation, and when it turns yellow, so the correlation is very strong. And now here in this case, we didn't yet use the valence and arousal information at all. So this is just normal intersubject correlation, and so we don't know exactly what is behind this, so it's all driven by the film, different events in the film. And so then we take the valence and see so where the similarity co-varies with the valence of the stimulus, and here we see those areas. Perhaps we don't look at these detailed areas and discuss about them so too much, but whenever the valence varies, and especially when the valence goes down, when we feel more and more negative. So then activity increases in these areas. Posterior superior temporal sulcus, insula, and medial prefrontal cortex. So basically these are areas which are always implicated in emotion-related experiments. And so when you then co-vary, so the similarity with arousal, so this is what you get. So to make it very short, so what is important here, that even when very often valence and arousal correlate with each other, so the brain level, so the mechanisms are different, at least when they are so estimated in the way how we did it here. So this is a very exciting experiment, and so I really hope that we can continue this line. So this is about contagion of emotions from speech, brain-to-brain connection. So the paper was published just a couple of months ago, but we actually worked with the manuscript for many years, because actually it seems that this kind of doing a cognitive neuroscience is not easily accepted in the field, at least at the moment, but the situation is changing. So we tested whatever emotional contagion, whether emotional contagion between two individuals is associated with enhanced intersubject neurosynchronization in a two-person pseudo hyperscanning setup. So two speaker subjects told emotional and neutral autobiographical stories while their brain activity was measured in the scanner. So now we can actually think that there was just one speaker. And then the stories were recorded and played back to 16 listeners. So this is the setup. So we have the speaker, we have the listener, and so we record the speaker's brain activity. And so the point is that on the basis of this activity, we try to predict the listener's brain activity. And as you see already here, this works. So brain-to-brain coupling, and of course assuming that these two people are using somehow similar mechanisms in the brain for production of speech, thoughts, ideas, and understanding them. So this is of course the difficult part, but more or less this works. So the stories were 1 minute short episodes based on autobiographical memories, and then as always then we also asked the subject to estimate the arousal level and valence level the stories. And this was done both by the speaker and the listeners. So here with the black color you see the estimation of arousal by the speaker, and with the purple color by the listeners, and also the standard error, the mean there. This is for arousal and this is for valence, and what we see here is that actually these go very nicely. So emotional state, the speaker, and emotional states, the listeners, are similar. which is a good thing. So then similarity of both single time courses, I don't show this again. And examples of stories. So pleasant story was something like that, or was like this. I was lying on a blanket underneath a tree with my lover. We were kissing passionately and I felt I was so much in love with him. Very nice and positive story. Neutral story, I was spending the afternoon at home and so on. And then unpleasant story, I was sitting on my mother's hospital bed. She had fallen into a coma during an unsuccessful operation. She could no longer talk to me and I knew she would never recover. So very sad story. And actually the subject rehearsed to tell these stories at home so when we scanned their brain, so it was easy for them. That actually was a very important part of the experiment and made it very, very hard. And speakers were encouraged to vividly imagine the events and rehearse each story so that they could narrate the stories effortless in the scanner. So this is direct speaker-listener correlation. So kind of simple without taking into account now the emotions yet at all. Oh, sorry. Okay. So it's not my sound. It's
yes, I get it. It shouldn't be that sound.
No. So it's not my sound. It's sound of this device. It's exploding.
It's you see the signal from the HDMI. Can we just stop for a while?
So like this. So it's not my sound.
I get it. Okay.
Sorry. Right. Now I'm feeling neutral. Very neutral. Right.
Okay, let's
But things happen.
go again. Can we see?
Yeah.
Start.
So now this is right. So no problem. So things happen. Don't worry, be happy. I was told many times. It's coming. Okay. So this was the direct connection between the speakers and the listeners. So there's a direct connection even when we don't care about the estimated level of the valence and arousal. So there are many things which are, of course, not surprising. So you would expect that when you speak, your auditory cortices are activated in the left and right hemisphere, but actually this hasn't done before. Actually predicted activation of your auditory cortex on the basis of my auditory cortex. So this is why it's nice. And some other structures also there, which you can, the details you can find in the paper. So we have a look at those areas where this similarity depends on the arousal level here, and now we see more restricted constricted pattern of activity. Premotor cortex, angular gyrus, somatosensory areas, somatomotor areas, supplementary motor areas, and so on. And when we go to the valence, we see a set of other areas. In temporal polohesal gyrus and so on. So once again, actually, when it comes to emotions, it's always the case that it is a very extended network which underlies the emotions. It's not a certain structure. For example, it's not amygdala. It's a very complicated network of activity and so especially is found in the midline structures of the brain. So this is now really interesting part of the story. So this shows the neural correlates of similarity of emotional feelings of speaker, listener, pairs. So when we are tuned emotionally, so this is reflected in these areas of the brain, and I believe that okay, here, warm for valence and blue for arousal. So we have at SPL, somatosensory cortex, so anterior cingulate cortex, for example, and precuneus, of course, because nowadays always precuneus are activated. We have similar activity when we are feeling the same emotional valence. And with the blue color, for example, here we see fusiform cortex, this B2 areas, so secondary visual area, and some other parts of the brain, so which are then similarly activated, so with the arousal level of the emotion is similar in our brains. And so to add a little bit here, so we have also shown that actually the more similar are the felt emotions, also the more similar are the neural mechanisms underlying these emotions. So it's not the individual computation. So it's also shared computation, partly. So similarity of emotional feelings across speakers and listeners quantified as arousal and valence is associated with similarity of neuronal activity. So a couple of areas, perhaps we don't go to them, so you can check them from the paper. And the conclusion from this experiment is that emotional transfer emerging during verbal communication is accompanied by a regionally selective synchronization of the speakers and listeners' somatosensory, limbic, and attention brain circuits. So when we talk both on valence and arousal. And similarity of emotional feelings across speakers and listeners was further associated with increasingly similar neuronal activity in the somatosensory, parietal, subcortical, and cortical midline regions. So this brain-to-brain coupling. So similarity in the brain activity predicts the similarity in the emotional state. So to complicate things, of course, it's good to complicate things because then you realize that so we don't understand yet very much, even when we have these wonderful methods. So we are also studying how we understand the other person. So specifically we are studying design interviews. What we measure there is called empathic accuracy. And so I don't know how much you know about these measurements, but so when two persons who don't know each other, so meet in the cafeteria and drink coffee and start discussing with each other, it has been estimated that they understand 20% of each other, what the other person is saying to them. But we have the illusion that we understand 100%, right? So in our experiment, so we have a very special case design interviews, so this understanding of the other person goes up to 50%. But can you imagine what is still left there? And we believe that so we understand the person. We can make inferences, what she's thinking, how he or she is feeling emotions. This is what we think, but so we are very often very wrong. And so how to take this into account when it comes to our brain measurements, so needs to be seen in future experiment. But I believe that so this is very, very important point to realize, always related to the communication, real communication. So observing reality is subjective and contextual. So this is my another favorite topic. And so we have used the same film stimulus in all these experiments. So this is the film stimulus. It's about the moral dilemma. So these two sisters, so are the main actors. They're Kate and Anna, and Kate is seriously ill. So there's a moral dilemma, which we chose because we wanted to especially study those brain mechanisms which are related to the processing moral dilemmas, to be specific. So with our research questions. So then we actually did some manipulations. So we told to the subject before presenting the film that the protagonists, so the sisters in the movie, are adopted or they're genetic sisters, to make the comparison. So do they see the film in the similar way, so when they think that so the sisters are adopted and genetic sisters? The subject reported that it doesn't really matter. I don't care, so my feelings are exactly the same, but let's see what happens. So then we also ask the subject take the perspective of Kate or Anna. So another kind of perspective, way of perspective taking. So then, we also studied the subject having different relationships. So of course we studied one subject actually 4 times, and you're assumed to be similar to yourself, right? Of course, sometimes it's not the case. But so we also studied the sisters and friends and acquaintances, and especially now what I will show is are the brain patterns of the sisters more alike than those of the sister and an acquaintance. So what kind of difference it makes when we have lived a similar life, more or less similar life, and experienced the same things by living in the same family. And so then also we studied with our great colleagues, Yuri Alexandrov, so what happens when the subject have different thinking styles. So this is once again inter-subject correlation across all the 30 subjects across conditions, and once again we see the pattern of activity which you are expected to see when you're seeing a film. Exact pattern, of course, depends on the contents of the film. So what we always see a very strong activity in the speech-related and auditory cortical areas and the visual cortical areas. But in this case also in the motor cortical areas and then of course the parietal areas. And so midline structure is very strong. But this is what we see when we compare. This cueing, so that the subject were cued, so that the sisters are genetic versus adapted. And now with the red color you see those areas where the similarity is related to the knowledge that the sisters are genetic, and with the blue color, where the sisters are thought to be not genetic. So there's much more extensive activation, in the temporal cortical areas, but also in some other parts of the cortex, but especially here at the midline structures. So it makes a difference at the brain level. So then the subject takes the perspective of Kate versus Anna. Kate is suffering with a pain in cancer, and Anna is refusing to donate her kidney to the Kate. So you take the position in the film, one of these actors, and then this is what you see. So when you compare Anna's perspective and Kate's perspective, a little bit different. Pattern of activity compared to the previous one. So now once again with the red color you see, increased similarity. So when you take the Anna's perspective, and with the blue color when you take the Kate's perspective. So even this manipulation influences how we see the film, and of course, whenever we see the film, we see it under our individualistic way. But on the other hand, we can talk about the film with our friends. So we have both individualistic way of viewing the film and shared way of viewing the film. And so these are the brain areas where activity becomes more similar, the more related the subjects are. And so we are still actually working with this manuscript, but this shows the linear increase in the similarity of the brain activity when we move from the sisters via friends to acquaintances. So more similar, we can assume that the background of the subject is, the more similar is their brain activity in the areas showed and marked here, both at the cortical surface and at the midline structures. And so the last part, so you remember that now this is just one film, and we are manipulating various aspects there, and also studying the cognitive style of the subject. And so this is from the last part, studying the differences in people who show holistic thinking or analytical thinking. And why now important thing is that all the subjects are Finnish subjects. They are not, for example, Russian and Finnish subjects, but they're all of Finland, which means that more or less their cultural background is similar. Of course, there are similarities, but this is kind of cleaner, relatively clean, indication that the thinking style, so influences how you see the film. But not some other factors which are in different countries, for example, might explain these effects. So perhaps I just go on, and I don't go to talk about those brain structures, but conclude that in trying to make sense of social interactions, what we know, so in trying to make sense of the social interactions, it influences what we know of the individuals. Background information, context situations, whose point of view we take, right? So perhaps it's switching all the time, and this is why it may be actually so influencing also all the time. So what the results, what we get from our experiments when we use these complicated stimuli, is shared with people close to us. So the closer a person is to us, so the more similar is our thinking of the world. So I'm sure that everybody has a lot of experience in that, and also so how we see the film depends on our thinking style. So in this case, so if this thinking style is holistic versus individualistic. So then, how much time do I have?
You still have 15 or 20 minutes.
15 or 20, okay. So tell me, so when we are in 15. So this is now we go more closer to the ground. So I tell you about our recent studies on lip reading, listening, naturalistic narratives. So we have lip reading stimuli, so lip read stimuli and auditory stimuli. And so in the fMRI scanner, so we have 30 subjects, so which perceive these different stimuli. And the point is that lip reading skills of the participants varied extensively, so which were measured before scanning in the sentence test. And so this is what you normally get actually. People are lip reading skills of the people so vary a lot. There are a few people who are really good in that, but most of us are really bad in that. Of course, once again, so it depends. So your families, for example, if your parents were deaf, so then you had to actually learn it to do it better. So the stimuli were intact and gibberish narratives. So gibberish auditory narrative sounded like normal Finnish, but was incomprehensive. I don't explain how they were made, but so they didn't make sense, but they sounded like perfect Finnish. And so gibberish lip reading narrative depicted the speaker to read the gibberish narrative. And so once again, so intercept correlation was calculated, and so these are the stimuli. Let's see, or here. Where was my sound?
You're lip reading, right? You don't read the sound.
I'm sorry. Sorry, my mistake. You can go away. So now this is critical.
Havahduin herätyskellon sinnikkääseen pirinään. Herääminen tuntui raskaalta. Havahduin
This is normal Finnish language, but listen to this.
Hapaktuin kenäsyshellon tillikkääseen mininään. Kelääpinen surtui lattialta, pussamakotin estini yröstätkystä. Tapputin iriä äältämisären kenäsyshellon, kaperyttelin ketken. Muuriruhu.
Where our stimuli. And so here we see, what happens in the brain when the subjects are now listening to these narratives, so kind of relatively normal pattern of activity, of course, extensive activation in the left and right auditory cortices. What is kind of so important, so is that so whenever you use this kind of naturalistic stimuli, then usually you get actually very bilateral activity related to the speech. So this was originally shown by Uri Hassan, but this we have seen repeatedly seen the same thing. So what is interesting, so we are now thinking, so should we actually more carefully study what is happening in the cerebellum? So people are more and more interested in the cerebellum, and we also imaging that part of the brain, but also then in the midline structure. So this is listening pattern, and this is what happens when the subjects, all the subjects are lip reading. So this is kind of so intercept correlation across all the subject, independent of the lip reading skill. And so there's a huge difference, as you can see. So now, so of course it depends also on the statistical significance level, but if you have the same level in both of these cases, you see just a couple of spots here, so where the subjects show similar activity in the brains when they are lip reading, and of course you would expect that so these areas have to be the visual cortical areas, right? So, but what we did next, so we calculated the neural similarity of lip reading and listening intact narratives. The reason being here that you have to now understand that when you calculate the intersubject correlation, you in a way you actually use another person's brain activity as a model of the other person's brain activity. There's no stimulus model. There's a brain activity model. So it's a simple correlation what we are calculating. And now we thought that probably the case here is that actually the signals related to the lip reading are so small so that they don't provide, because the signal to noise ratio is a good model. And we decided to look, what happens when actually couple, the brain activity during lip reading and brain activity during listening to intact narratives, where the activity is similar. And this is where we get actually a much more complicated view. So what parts of the brain are activated during lip reading here on the left and right. So side of the brain, and once again, of course, the auditory cortex is different part of the auditory cortex, motor cortical areas, and precuneus, and also visual cortical areas. And what is kind of conspicuous thing is that precuneus seems to be implicated always the subjects are listening to the stories. Right. So here we see once again this lip reading across conditions and listening within condition, and to compare how the brain activity differs in these two presentations. And what is very clear that the activation pattern is not so extensive and not so strong during lip reading than listening, but on the other hand, you see many similar areas activated during the lip reading than during listening to the story. So here we actually show the areas where neural similarity correlated with lip reading skills. So these people are good lip readers. So good lip readers are similar in activating their left and especially right auditory cortical areas. Why is that? And actually I will suggest something. And here we see the brain activity patterns during lip reading and listening to gibberish narratives. And when you're listening to the narratives, you get activation in the speech areas, auditory areas, probably because this is kind of natural sounding Finnish speech, which activates your phonological processing mechanisms. Also it activates, of course, perhaps visual parts of the cerebellum and the visual cortical areas. And when you're lip reading, and once again, comparing lip reading to the comparing lip reading to the listening, then you get activation in these areas. Perhaps we don't talk about this anymore. So the summary is that lip reading and intact narratives activate many similar areas in the brain as listening to the narrative, but to a much lesser degree than listening. And lip-read narrative was poorly understood by most participants. So this probably explains this. So skilled lip reading is specifically associated with bilateral activity in the superior and middle temporal cortex, which also encode auditory speech. So perhaps this is related to the fact that these subjects have a good phonetic encoding in general, also related to the understanding spoken language and speech. So it could be related to the phonetic awareness, because there's evidence that actually good lip readers have a very good phonetic awareness. So what was kind of curious was that listening to narrative activates occipital midline visual cortical areas, not foveal areas. So this is kind of interesting finding, which probably just shows that so whenever we listen to the stories, so we need actually visualize the things in the story, and this is probably why so we always get also activity in the visual cortical areas. So lip reading gibberish activates auditory areas bilaterally, but much less than listening to gibberish, and listening to gibberish perhaps activated areas related to the phonetic processing, because gibberish was phonetically valid Finnish. So next step in this so data set is to use language model to be more specific of which aspects of language processing are reflected in different brain areas in intercept correlation data. And so this is what we are doing with our phonetician colleagues, because they're using actually having models of the speech sound at different levels, and then we use this as a correlate to understand more specifically what aspects are we have seen here. So now I think that I have to, with something, so perhaps it would be good to go to the perhaps conclusion so that we have some time to discuss. What do you think?
It's up to you.
Okay. So perhaps, this is nice. This is perhaps nice. So homophily, mental similarity created by culture. So how that is reflected in brain, this is of course kind of continuation of the story, and this just shows that so when a group of friends meet each other after, let's say, 20 years, they sometimes have very similar clothing. So these are typical Russians. These are typical things. And as you can see, actually, there are some differences, but there are a lot of similarities also. So I have actually shown now these figures here because so this was actually one idea behind the experiment, what we did. So people raised and living in a shared cultural environment tend to share similar knowledge, experience, beliefs, values, attitudes, and social habits. This is, of course, pure sociology. We use the sociological knowledge and information to study what might be happening in the brain, so when this happens. So does shared ethnic, cultural, family background shape processing of natural connected speech? So this is in progress in the sense that so we didn't yet get it published, but so we had 24 residents of Finland with a Finnish family background and 25 residents of Finland with a Russian family background. So the thing being that actually all the subjects were fluent in Finnish. They spoke perfect Finnish, independent of the family background, and so then all participated in a functional MRI study, so which was an ultra-fast fMRI, but actually this is not very important now. So we are still analyzing the MEG-EG part of the experiment. So perhaps the point just to mention here is that so we get figure of the brain activity at the slow rate and at the fast rate. So and when you're interested in what might happen in, for example, auditory cortex, so then the MEG-EG becomes very important. So the subject listened to the experiment, had different backgrounds, and then so after the experiment we make an association experiment, so where the story actually, which is a long story, 70-minute story, so it's stopped every now and then the subject actually had to generate mental associations related to this part of the story. So individual perception of the story, so to say. And then what we do, of course, is that so then we have actually the measure of the similarity of the brain activity, and then we have the measure of the mental contents between these two subject groups. So Finnish background and Russian background subjects, right? So this just shows the behavioral part of the results. So in 45% or 45 episodes, 110, if I'm correct. So we didn't find differences between the Russian background and Finnish background subject. But so in 44 stories actually. So subject with Russian cultural background produced more similar associations, and the same was true for 12 stories for Finnish subjects. So there's a clear difference here. And it also was so that the Russian background subject produced more words to describe what happened in the story, which is interesting. Perhaps it's related to the fact that they are multilingual because they speak both fluent Finnish and fluent Russian. So here you see the differences. So colored with warm colors, with the red and yellow, you see those parts of the brain where the Finnish background actually produced more similarity in the brain activity, and with the blue color, so with the Russian background, so produced more similarity. So in temporal areas, and so this is where we could argue that probably so this cultural background influences sentence and word level semantic processing, because so these areas are implicated in this kind of processing in many other studies. So precuneus, which is always activated, so when you listen to the long stories, which is related to narrative level processing. And then occipital cortical areas, so perhaps it's related to the visual imagery. So perhaps this is self-explanatory. So even people who command Finnish language very well, which means that actually what we find here probably is not so much related to the language and skill of the language, but it's about the background, how they have used the language in their circumstances in the family, and of course also with a friend. So we don't have more detailed description of the subject. What exactly is the main explanation here? So it remains open, and this is very often the case with this kind of experiments. So I just show the last slide here before going shortly to the conclusion. So we also jump to psychophysiology during conversation, and so this is how it goes in conversation. Two subjects are telling stories to each other, and then we measure the physiological signals and study then the correlation between the physiological signals. So this person is telling, and this is affiliating and listening to the story. And as you can see, this is not heart rate, I believe the GSR, what we are measuring here, and now it's reaching its peak.
Jotenkin niin sellainen voimakas kokemus, vaikka ei se siis silleen, jos mä hyppäisin uimahallissa, niin ei se olisi niin siistiä, mikä jäisi mieleen, mutta
So, because this is collaboration with people doing conversation analysis, so then of course they very carefully analyze the structure of the conversation. It takes days. It really takes days, so it's good to have this kind of collaborators. So, and actually they're very good in this. And so this is what they do. So transliterate all the story, and then they mark different parts of that. And then of course we also try to see physiological changes related to specific elements in the story, but so then very often we have the problem with the statistical power in our experiments. So what we find constantly is a very interesting thing, is that we have found that in 3 separate published experiments that arousal level, especially of the storyteller, decreases when the arousal level of the listener increases. So I tell a story to you, and you carefully affiliate and listen to my story. It makes me feel good. I tone down my arousal level, but so the person who is receiving the story actually gets more tensed, more stressed. And so I like this expression very, very much so we have called it sharing of emotional load. And this is probably what very often happens actually during normal conversation, but also in therapy. And this is probably also when you're a therapist, you need actually to do something, because otherwise the load actually could become too hard for you to take when you do this on a daily basis. So now we go to take home, and then very soon we are free. So intercept correlation analysis allows studying brain activity during perception of rich real life-like stimulation, and I'm more and more going to this direction. There's so much to be done, and things look very different when you go to the real life, but of course it's hugely difficult enterprise. So the background state of the subject strongly influences how the brain processes such stimulation, and I'm so worried about this. we should be so much more careful, at least we, I don't talk about you, in actually so knowing so how the subject relates to the situation when we present to him this very complicated story. Probably it's also true when the stimulus is more simple. But in our case, it's extremely important, and so there's a long way actually to go to have that in control. But we are going there, especially with my performance artist friends. Skilled lip readers use the phonological processing systems. Speech is perceived in an individual way at many neuronal levels, right? And emotions amplify speaker-listener neural alignment. So these were the main points. And future directions. So what we would really need is kind of automatic or semi-automatic tools for annotating films and narratives at different hierarchical levels. This is the hard part. So when we use intersubject correlation, so in a way we ask the brain to tell how you're processing the stimulus. But what exactly is then happening around, so the subject here, that's the hard part. And so if we could, for example, have very good automatic tools actually to do it for us, and then just actually to check them, so that would be very helpful. So luckily they are more and more available. So many people are working with this in Google and there are many other places. So easy professional production of narratives and films. So actually so of course we can use commercial films, feature films, but actually if we want to address some specific questions, so this is crucial thing, and we're also actually working with these things a little bit. And when it comes to narratives should be really good, and there once again you need actually a good scripter and also a good speaker, so that they involve the subject as well as possible as in normal life. And so I'm convinced that we should move towards single subject studies. So because of various reasons, and one reason being that always when we do this kind of experiment, we have a problem with functional anatomical differences in individual brains. And this is a very serious thing, but the problem is that it seems that at least cognitive neuroscience, community doesn't like this approach. So you want to have, we started with 7 subjects, then 12 subjects, 20 subjects, 36 subjects, now it's 100 subjects. In my opinion, that's nonsense. It could be okay in clinical research, but I would go actually to single subject studies and then add a couple of other subjects to know the behavior of one person, and especially his or her brain and bodily behavior as well as possible. And finding out what is replicated during different complex stimulations. Because when we make the speculation, so what the brain activations means, so of course it can be also related to the specific stimuli what we are using. We should always repeat the experiments using different materials, but as you know, we also need to publish, and this is why everything takes so much time. It's not a good thing, but we have to be streetwise to survive. And in this kind of experiment actually, interdisciplinary collaboration is so important. And I have really enjoyed it, and I've also realized how difficult it is, but especially collaboration with sociologists and philosophers has been really influential for me. My feeling is that very often cognitive neuroscientists think that sociology, that's easy. You just take your book or your paper and read it, and then you know your sociology. But I believe that it's not the case. You have to be a professional sociologist or philosopher to contribute to this research. And then actually, when this starts working, this is really great. So these are my great collaborators, Satu Saalasti, Enrico Galerian, Juha Lahnakoski, Iiro Jääskeläinen, some of you recognize Iiro, Mareike, Uri Hasson from Princeton University, actually, who is behind the intersubject correlation calculations, great scientist and actually involved in these lip reading studies. And my great friend Jura Alexandrov, very seriously there. And then Maria Hakonen, who is actually now just finalizing her thesis, and this is Dima Smirnov. Actually was involved in this pseudo hyperscanning experiments, and Heidi Saarimäki, great emotion researcher now as postdoc in the United States, and Riitta Hari, my great collaborator, doing decades. And my last slide. Sorry to make you tired. I fully understand that you don't want to ask any questions.
So thank you so much. It was wonderful, as always. So any questions or comments in spite of the shortage of time? So quite a lot. So let's start with you. You were the first.
Thank you very much. Actually, your idea to calculate the level of understanding is very revolutionary, because we all wanted to do that, but how do you calculate it? And because understanding is a very complex thing, and there are different elements in understanding, and content, and valence, and everything. And tell something more about that.
I will. So we have the project called Empathic Engineer. And so we have, in this project, we try to understand what empathy really means, because so empathy is, at least in Finland, used in a very loose way. Everybody talks about the empathy and importance of the empathy, and perhaps they can make a separation between emotional empathy and cognitive empathy. So, but in my opinion, it's much more complicated thing. So usually people, when they talk about the empathy, they talk about being a good person. So being nice and smiling and trying to have good interaction. So I was very happy to realize that actually there's a method called Empathic Accuracy, which refers to the method, so which can be adopted in many ways. But so this is how we are doing it. So we have a designer, and then we have the end user. So the end user, so our case was actually a musician, and so the musician is telling about his work as a musician, so about his instrument, how he's dealing with the instrument, problems with the instrument, and so the designer actually is talking with him. And then we of course video everything, and we also have sensors, so that we also physiology, and then we take the video and show it to the end user, and ask the end user always stop the video when he has a strong feeling that he remembers well, what was his or her mental content, what was in his or her mind, what was in their mind, at that moment. And so during the interview they do that, let's say 20-30 times. Even so, it depends on the subject. And then we ask the designer to view the same film, and whenever the end user stop the film, then the designer is asked to speculate about what this person was thinking, what he was feeling, what they were feeling, what they were thinking. And then we just make the simple comparison. So then there's independent group of people who are then studying the similarity, and then we scale that. So I'm sure that you can do that better, but I was just happy to realize that there's at least this one published method which has been used before in the similar interactions, and it seems to work. And our actually level of understanding is now at 50%. So the thing here is, of course, that if you want to do some intervention, that if you want to increase the design process, you have to be able to measure what is happening there. Otherwise, it's just hand waving, and so it doesn't help very much.
Thank you, sir. Okay.
So, wow, thank you. Such an incredible talk, and so many questions, but I'm going to limit it to one that I'm a little confused about. So in the movie watching, when you had the negative valence, you found amygdala and thalamus similarities. So it's not activity, it's similarities and patterns of activity, right? So I'm with you so far, yeah?
Okay, so refer to the both
valence.
Valence?
Yes.
Yes.
Okay, so then when you did the study where it was sisters and they were adopted versus genetic versus friends, and you had the closer the similarity, I was surprised not to see, so I was thinking of it as, okay, this is a study of the moral areas of the brain and it has nothing to do with the activation necessarily, but if you would expect somebody to be sisters, I would have expected to be more empathy. And I would have expected more similarity in emotion. And I wasn't seeing emotional areas lit up.
Okay, so this, of course, this experiment, so it's a very complicated one. So because when we studied actually the relatedness of the subjects, actually we collapsed all the conditions together. So then we don't know it, we couldn't anymore so separate these different manipulations there. So probably if we would do the same thing, taking into account, for example, the moral dilemma, so then probably we would start seeing this kind of things. It's very much how exactly you analyze the data. Another possibility, because this, it may be also related just to statistical power, because it may vary a little bit between the different comparisons. So it's better to look at it very carefully so did you see my point? So that we collapsed all the conditions together, so then that might actually explain it now. So because it was not involved in all of the conditions, perhaps.
So the finding that the arousal of the speaker kind of goes down when the arousal of the listener goes up sort of reminded me of work on temporal difference learning, where like at first you have arousal to some kind of actual biologically relevant event, and then as you learn predictors of that event, that arousal peak goes earlier and earlier and earlier until it sort of occurs at the earliest predictor, right? So I'm wondering if that's sort of going on here, and that maybe the speaker is already anticipating the climax of the story before the listener hears it, right? And so their arousal peak occurs before the actual climax, and then the listener hears the climax and on arousal peak.
Planning.
Might be. So now, one thing here is that, of course, the time resolution of this signals is very poor. That actually, we have to actually have a relatively large time window, so within which we are looking at the things. But so this is a good point.
I really like the approach, but I wonder whether it can be making it more sophisticated, because as you say, you recognize there's a lot of anatomical differences across people. So,
right.
So essentially you're making their brain similar by warping them into the standard brain.
Right, yeah.
They vary in size, and not only in size, they vary in structure. So sulcus and
Absolutely.
gyrus, they're
Yeah,
all going to
yeah,
be completely
yeah.
different across people. But that side apart, if you correlate and say my activity with someone else's activity, by default, you're going to get a huge number of significant correlations. Not just because of the fact that by chance you'll get a lot, because we're talking about how many voxels in these matrices, thousands, but also because our brains are similar in structure. And the ball response is recorded from very similar structure. So the vascular structure of the brain and the white matter tracks are the same. The gray matter is distributed in similar ways. So I would expect a default correlation already very high. So what I would like to see is to test the similarity across my brain and his brains over and above the similarity that I would already expect, right? By the fact that we have the same structure, the same gyra, the same sulcus, the ball response is noisy, everything else.
Right. So, of course, you're correct. And so, yeah. So when it comes to the first part of your question, so there are ways, of course, in trying to make the standardization of the brains in a good way. I mean, use localizers and things like that. So we should work much more on that. But so it would be very important to have a good set of localizers, but so then localizing it, so the individual brain, so probably would take quite a bit of time, but so then probably this one subject approach would be a very good one. So what you said, so last part of your question, so what is of course important here, that so we have actually changes in terms of correlation which are related, for example, some certain things, for example, emotional state, what is happening in the film, so they are not kind of very general things, but so they are So how the subject are perceiving the things, what is happening to them actually, so explains the correlations.
So following on from that, when you're looking at more similarity between sisters, right? Aren't they going to be more anatomically similar?
Actually, so we have tried to check it, and so they are not. Actually, they have. So even in identical twins, actually the brains are pretty dissimilar. So they are more similar than in non-identical twins. But so in this case, we did what we could actually to control this, and it didn't explain our finding. Yeah, but this is a very important point, certainly. I'm a little bit suspicious about were we able to do that well enough. Yeah.
One short question from me. What about the mirror systems in the sense of Risolati and Arbib? When you have that shared activity, how can you juxtapose it?
So I guess that actually, so this is one reflection of the mirror systems. Actually, you are kind of so using your own systems to understand what the systems of the other person are doing. So in relatively complex situations, in broad sense of the word.
Thank you. So, unfortunately, I have to say sad words closing this charming conference. Thank you so much for being with us these days. It's gloomy there, dark, but still quite warm here in all the senses. So thank you so much. Come back. Come back.